Hello, AP Stat peeps. Sadly, this is the last video, the last set of notes, the end of the packet, the end of the line for AP Stat curriculum for the year. If you're emotional right now, as I've said in the past, take a few minutes, pause this video, seek counseling. All right. Otherwise, hey, let's finish off what we need to talk about. All right. Okay. So we are in 12.2 now. All right. I know my last video was a little long and a little wordy, as with anything and during this time period. If you have any questions at all, feel free to email me. We can set up like a Zoom or something if you want to talk, or I can certainly answer questions you have on anything. Homework questions are great practice and obviously a good foresight for what you're going to see on the test. So feel free to take advantage of those as you might always. Okay, so let's talk about transformations to achieve linearity, kind of the last small section here. It is part of the AP curriculum to talk about transformations. Not that often are questions asked about this, but it has shown up, especially in some FRQs a couple of years ago. I know 2 or 3 years ago, there was a question regarding transformation. So it is something you need to be aware of. All right. And I think it's kind of cool, actually, because what if, and you see in this little scatter plot right away, what if a linear model is not appropriate for analyzing a particular relationship between two variables? All right. So when associations are nonlinear, we can't take advantage of all the tools that we talked about in chapter 3. So what can we do? What can we do? All right. Well, one option is to fit a curved model. If you go to Stat Calc on your calculators and look at the different types of regression, remember 8 was a linear regression. Well, if you kind of spin through the options there's an exponential regression you can do. If you think the data looks exponential, there's a quadratic regression you can do if you think it looks quadratic. With more advanced software other than a TI-85, you can do other types of curve models that you can fit. So you can do a regression and try to come up with an equation that's not linear to fit data. All right. But the other thing we can do is we can transform / straighten the association. We can make it linear. Okay. Now, I guess the question is, how do we do that? Why would we do that? Well, why would we do that? Okay. Well, this would be the best choice because we have awesome tools for analyzing linear models and a lot more tools for analyzing linear models. So that actually is a little bit better route to go in a case where the data looks curved. Okay, so let's just look at a few examples here. So here you're looking at the this is a very interesting set of data, right? Atlantic Ocean rockfish. You guys think about these pretty often. So if you look at the length of an Atlantic Ocean rockfish and try to relate it to the weight, you'll see below. Okay, sorry, I'm back. The fam had returned with Chick-fil-A, so I had to pause there briefly. And just so you know, with Screencastify, which is how I'm doing these videos, you can only pause and resume from Chrome. So when I switch over to the dock camera, I'm going to switch back to do that. Anyway, all right, let's see. Get that autofocus a little better there. Okay. So yes, we have a scatter plot here. Length of Atlantic Ocean rockfishes versus their weight. Okay. Is a linear model appropriate here? Well, I don't think we need a residual plot to tell. All right. That is a no. It's obviously curved. Okay. Now, if we were to fit a curved model, what does this look like? Now, typically, our choices are going to be one of two things. Okay. So it could be an exponential model. Okay. Or it could be something that we call a power model. All right. And a power model means we are looking at y equals x to some power. Okay. Exponential obviously is something different. It's y equals e to the x or 10 to the x, or I'm sorry, y equals log base e or log base 10 of x or something like that. Anyway, so if we look at this, I mean, what do we think? Exponential usually means that we have a curve, right? But it rises pretty quickly if it's exponential. So this is rising pretty slowly here. It's curving up pretty slowly. So maybe exponential is not maybe a great option here. So why don't we assume that maybe this is a power model? Okay. Now, we could maybe guess it's quadratic. What we're going to do here is assume that it's a cubic. All right. And you could try all different powers, but we're going to do cubic here. Okay, just to kind of show you how this works out. All right. So, oh my gosh. Okay, my reading glasses have disappeared. Let me pause, please. I'm back. They were 3 feet away from me. All right, so there's several ways we can attempt to linearize a curve dissociation. And it mentions this here in the notes: powers, roots, logarithms. So we're going to look at powers first here. So if we think that might be a cubic looking curve, the right side of a cubic graph right there, then what we could do is sketch y versus x cubed. Okay, and so that's what we'll do here for this example. Look what happens. Notifications go away. All right. So what we've done here is we've graphed length cubed versus weight. Look at this. Now it looks very linear, right? If we graph length cubed versus weight. Okay. All right. Well, that's wonderful. Here's the computer output for length cubed versus weight. Okay. We could write a little equation, a linear equation, right? Okay, because here's our y-intercept, here's our slope. All right, so we could say the predicted weight is equal to our y-intercept, 4.066, plus, and our slope is right here, 0.014, etc. We'll just round that to maybe 0.0147 times. Now, instead of length here, it's going to be length cubed. Okay, so we have weight versus length cubed. Looks like a pretty strong linear model. Well, let's look at some of these things. Standard deviation of the residual, 18.81. Look at R squared. 99.5% of the variation in weight can be attributed to this model. All right, versus length cubed. So bingo, looks like we're on to something here. Looks like a great way to linearize this particular model. Okay. Now, what if we want to make predictions? Okay. So here's our linear model, our equation, our LSRL. All right. It says here, predict the weight when the length is 36 centimeters. Okay. Well, this is pretty easy. We're just going to plug in, 36 for the length. But remember, we're having to cube it here. Okay, so we're just going to put 36 cubed there. If you do all the math, we predict the weight for a 36 centimeter Atlantic rockfish to be about 689.91 grams. All right, So that's one example of straightening the association. All right. This time we did it with a cubic model, a power model that's cubic. All right. Well, is that perfect? Is there a better way to do it? Well, let's see. Okay. So here's another example below where instead of doing y equals x cubed, because we're liking that cubic model, what they did here is they graphed the cube root of y versus x. Okay. So it's kind of like taking the previous model and taking the cube root of both sides, right? Well, how does that work? Well, we would have the cube root of the predicted weight is equal to our y-intercept. And again, this actually looks like even a straighter line than the one above. So our y-intercept would be negative 0.022, round that a little bit, plus our slope is 0.24, about 7 times the length. Okay. Well, why do we do that? Is that any better? Yeah, look at S. Oh my gosh. S is 0.124. Look at my R squared, 99.8%. All right. So even more of the variation in predicted weight, cube root of predicted weight, can be attributed to this model. So this is actually even a better model than the previous one. Okay. All right. Let's try to predict the weight when the length is 36 again. Well, if I'm going to do that, then we'll plug in 36 for the length, 36 centimeters. All right. If I do the math there, then the cube root of predicted weight is about 8.87. All right. So if I want to solve for weight, then I just have to cube both sides, right? So then predicted weight is going to be equal to 8.87 cubed. And I get 697.86 grams. All right. Notice how that's pretty close to the prediction we made for a 36 centimeter Atlantic Ocean rockfish up here. Okay, but a little bit more accurate model here, a little bit better R squared value. So this might be a better prediction, a better estimate. Okay. All right. Again, I apologize. Let me pause 1 second. My daughter is not doing something that she should be. Okay, sorry. Yeah, I have a 16-year-old that's e-learning as well. That's forgotten to Zoom one of her teachers. All right. Okay, so let's go back to this example that we just talked about. So again, here we straighten this association one way by doing y equals x cubed. Here we did it a very similar way using the cube root of y versus x. Got a little bit better association, a little bit stronger association. And at some of the stuff with doing transformations and strengthening associations, in some cases it's just a matter of trying different types of models and types of transformations and see what gives you the best fit. And again, looking at S, looking at R squared are great ways to assess that fit. All right. Okay, last page of the notes. Okay, so same thing, Atlantic Ocean rockfish, length versus weight. Okay. All right. So we think a power model works good. Let me get this down. Okay. And we really like the cubic, and that did pretty well. All right. Now, if you think a power model is appropriate, if you think it's quadratic, cubic, quartic, something to that effect, here is actually the best way to transform. So look at what we've done here. Okay. Here we are graphing log base 10 of length versus log base 10 of height. Okay, so log of x versus log of y. Okay, all right. Again, very strong linear association. If we go here Look at S, tiny, tiny S, 99.9%, pretty much 100% of the association. I'm sorry, the variation in the log of the weight is attributed to this LSRL. Okay, so this is actually even a better model to straighten this association. Okay, so let me write that first, because when you're doing a power model, or when you think a power model is the best choice for your curved relationship, then do log y versus log x. And when I say log, it could be log or it could be ln, natural log. We use those obviously because those are buttons on our calculators. So for a power model, this is what you want to use. And that's one of the big things to remember when thinking about transformations, all right, is what's the best transformation for a particular type of curved model, all right? Okay, now, could something else work better? Yeah, but log x or log y versus log x is always going to give you very, very strong associations. And as you can see here, it gives us the strongest one. Okay, how do we do predictions? Well, so now our equation is going to be the log of the predicted weight is equal to, our y-intercept is, looks like negative 1.899 plus our slope, in this case, is 3.049. And our x, in this case, is the log of the length of those fishies. Okay. All right, so to make predictions, it's very simply just plugging the values that we have, the x value that we have, into the equation and solving for the predicted weight. All right. So here we would just be plugging 36 centimeters once again in for x. So this is going to be log of 36. Again, you could use ln on both sides. It's just as long as you're using the same log base. Okay. All right, if you do the math, the log, the predicted weight, is equal to, this is about 2.846. Okay. Now, at this point, you have to know how to solve a log equation, right? This is about the most algebra that you have to do in this course. So remember, log with no base is really log base 10, right? So if I want to solve this equation for the predicted weight, it's going to be 10 to this power equals this value, right? So my predicted weight would be 10 to the 2.846 power, which is about 701.72 grams. Okay. If you look at what we did with the other models, again, it's pretty close. All right. The first time with y versus x cubed, it was 689.91. With cube root of y versus x, it was 697.86. Notice as our coefficient of determination, our r-squared value has gotten higher, so as our prediction. All right. So I would be most confident in this prediction of 701.72 grams for an Atlantic Ocean rockfish that is 36 centimeters long. Okay. All right. So that's power models. And that's a great way to do transformations for power models. Okay. I mentioned earlier that, well, it could be a power model, but it could also be exponential, right? And exponential looks a little bit different. All right. The curve increases or decreases a lot faster in an exponential model. Okay. All right, let me try to get a little bit closer here because the dots are a little bit harder to see. All right, different example here. So we're looking at time, years since 1970, and the number of transistors on Intel microprocessors. Okay, as you might suspect, as time has gone on, we've been able to fit a lot more transistors on microprocessors and make microprocessors so much smaller than they used to be. And so that number of number of transistors on microprocessors has risen exponentially. Okay. So very clearly, if you look at this curve, it's rising slowly and then it just shoots up. Okay. Very different from the more constant curve you saw in the previous example, which would indicate a power model. This one's exponential. Okay. All right. So with an exponential model, and I'm going to write this right here. Okay. We're not going to do a lot of experimentation this time. I'm just going to tell you that if it's an exponential model, the transformation that you want to use is log of y versus just x. Okay. All right. So you kind of get the exponential aspect of it thrown into the y, right? Because log is the inverse of an exponential. All right. And we don't do anything with the x. Okay. With the power model, the log y versus the log x, the exponential factor kind of cancels itself out, which creates a more even curve. Anyway, regardless of whether or not that makes sense, this is how you want to transform a model that you think is exponential. Okay. All right. So we've done that here. Not as great as some of the power model examples we did earlier, but you can tell it's much more linear. Okay. We would probably have to check out the residual plot just to make sure there's no obvious curve pattern. But if you look at the whole set of dots here, there's not really a consistent curve pattern. All right. If you look at the R-squared value, 98.2% is what that says. So really strong correlation, really small standard deviation of the residuals, a good linear fit. All right. So how would we make a prediction? Okay. Here we want to predict the number of transistors on a microprocessor in the year 2020. All right. Hey, that's this year, isn't it? Okay. So we use our data to write our LSRL. Okay. But with the y, it's the log of y. All right. This time I'm going to use ln. Okay. Again, ln and log are pretty much interchangeable here. I'm going to use ln this time. Let me move this over. So ln of the predicted number of transistors is equal to our y-intercept, which is 7.227. You see that right here. Plus our slope, which is positive, 0.3542. We'll just do 0.354 times, and this would be years since 1970. All right. Okay. So we're going to plug in for years since 1970. If the year's 2020, then that would be 30, right? Oh, I'm sorry, that would be 50. All right. 1970 to 2020 would be 50 years. Okay, that would give us a value of about 24.927. And again, to solve the log equation here, we just convert it to an exponential. ln is log base e, all right? So e to the 24.927 power would equal predicted transistors. Okay, so let me just write that. E to the 24.927, which is about, and you can do the math on your calculator, 66.9 billion. Okay. All right. So that's how to do transformations. And again, this page of the notes kind of summarizes it the best. For a power model, let's transform using log y versus log x. For an exponential model, let's transform using log y versus just x. All right. And then you can write lines of best fit, LSRLs, and then use that information to make predictions. Okay. That pretty much is a summary of transformations. Okay. All right. So one last little thing here. So there's 3 different scatter plots down here and 3 different residual plots. So below each scatter plot, you see a residual plot. Here we're looking at an X value of age, and Y is the premium for a cost of a life insurance policy, which is the best model to fit, and use it to predict the cost for a 44-year-old. Okay. All right. So here's just age versus premium. All right. If we just use the variables by themselves. Okay. Notice that the scatter plot looks curved. And if you look at the residual plot, there is an obvious curve pattern here. All right, I know you haven't seen a lot of examples of curve patterns in residual plots, but here's a pretty good one. All right, all the dots are curving down and then back up. Okay. All right, so notice here that they're doing ln of premium versus ln of age. I know it's pretty small, but so this is log y versus log x, something we would normally use in a power model. Okay, if you look at this curve over here, it's not really necessarily completely obvious if that could be a power model or an exponential model. Probably not enough points. So if we do ln of age versus ln of premium, look at the residual plot. All right, we still have a pretty good curve pattern. All right, these values go down and then back up. There's not a lot of scatter in the residual plot points. So a linear model really isn't appropriate there either. Okay, so why don't we use the exponential model to transform, which would be log of y versus x. Okay, our scatter plot looks pretty straight, and this time our residual plot looks a lot more scattered. All right, not really a obvious curve pattern here like there is here. Okay, so for these two, we have a curved pattern in the resid plot. So these are no good. Okay. All right, so we would use this one. This would be best. Okay. And so if we wanted to use that, delivery won't save restaurants, probably not. If we want to use that to predict, since that looks like the best model, the cost for a 44-year-old, okay? So now we're talking about natural log of the predicted premium is equal to, okay, the LSRL is down here, and it's very, very tiny. So let me write it for you. It's negative 0.063, that's that number, plus 0.0859, that's the slope there, times the age. Okay. All right, so if we plug in 44 for age, then the natural log of the predicted premium is equal to about 3.7166. So the predicted premium, since that's a natural log, would be e to the power of 3.7166, which is about 4112. Okay. All right. That's transformations. That's AP statistics for 2019-2020. There is a short assignment that has some questions on transformations. Check that out as well. Those assignments, I believe, are due Sunday night. And then go out to Canvas and look for basically the typical review resources that we post. So all Frappies for Chapter 3 and Chapter 12. The objectives, which reference review problems for Chapters 3 and 12. You have all of these notes and examples. Read every question in the notes and look at the answer. A lot of times the multiple choice questions come straight off of those. Make sure you know how to do the examples, the problems, and the exercises. And let me know if you have any questions whatsoever. Thank you. I will post some information on Canvas, an announcement, probably Friday, Saturday, regarding these videos. And we're talking about, like the 20th. And that way, if you want to get a head start, just finishing up Chapter 12, getting the exercises done, starting your review. Right now, we're looking at the test being the week after next. So we're looking at around the 31st of March for that test that covers Chapters 3 and 12. And then we'll launch into AP review from there. All right. Thanks, guys. We'll see you later.